All right, so to wrap up this section of notes here, we need to talk about similar solids. And what we do when solids are similar is the same thing that we do when two-dimensional objects are similar, right? They're still going to have a scale factor. Their linear measurements, if you compare them, are still going to be equal to the scale factor, that kind of thing. So first off, definition, similar solids, two solids of the same type with equal ratios of corresponding linear measurements, such as heights or radii. So equal ratios of corresponding linear measures. Any linear measure, right? As long as they're corresponding, they should be in the same ratio, equal ratios, right? That ratio is always the scale factor. Should be equal to the scale factor, right? So these guys here, the ratio of 7 to 21, which is 1 to 3, is equal to this ratio here, 5 to 15, which is again 1 to 3, and then 3 to 9 is 1 to 30, right? So those are all different edge lengths of those two similar solids. Right, this theorem applies, and we've talked about it a ton, especially with our area, it's two-dimensional area things. If two similar solids have a scale factor of A to B, then their corresponding areas are in the ratio of the scale factor squared. So you can even write this as A to B squared, right? It was the same as it was before. Surface area is square units. So then if we compare surface areas of two similar solids, they should be equal to the scale factor squared. Okay? We've seen this table before when we did our two-dimensional areas. It's still the same now as it was then, right? Parts, right? And perimeters. These are both linear measurements. So when you compare those between two similar solids, that comparison, that ratio, should be equal to the scale factor. Okay? Areas, especially surface area, is square units. So since this is square units, if we compare those two measurements, they have to be equal to the scale factor squared. Volumes we'll talk about later, but we've kind of mentioned it before. All right, first example. Tell whether the given right rectangular prism is similar to the right rectangular prism below. Right? If we're going to show that they're similar, then all of their corresponding linear measurements should be equal to the same ratio. Right? It should always be reduced down to the scale factor. So, for example, the 6 and the 4 would be corresponding. So the ratio of 6 to 4 would have to be equal to the ratio of 3 to 2. Which have to be equal to the ratio of 3 to 2 again. So obviously these two are the same. 6 to 4 does reduce down to 3 to 2, so those are the same. So then, yes, those two right rectangular prisms are similar. Okay? All right, now the idea of the surface areas being compared. Right, so we've got these two cans of peaches. The surface area of the smaller can is 51.84 square inches. And we want to know the surface area of the larger can. And we don't have measurements, but we do know that when you compare the two sizes, they compare to the scale factor of 4 to 7. Right? So if I want to compare the areas, 4 to 7 means I'm comparing small to big. So if I compare the areas, 51.84 compared to, well, I don't know the surface area of the big one, I have to be careful. These are surface area. These are units squared. That means that they're going to be equal to the scale factor squared. So you've got to square that scale factor. Now cross multiply to figure out that area. That surface area. Right? So now divide by 16. And the surface area of the big can is 158.76 inches squared. Okay, like I said, it's the same as it was with the two-dimensional areas, because the units are the same. They're square units. So if you compare them, they have to be equal to the scale factor squared. That's all there is to it. So this should wrap it up, and try some of those problems in your homework.